In this video, we'll cover isomers of coordination compounds. Take a look at this example over here. Here's cobalt with 5 ammonia and chlorine. That is within the bracket. So if I were to draw the structure, I will have cobalt in the middle, and I have two of them, two spokes going back. The squiggly line just means that it's going back of the page. And this wedge line represents that it's coming in front of the page. So it's kind of sticking out. And I'll draw all the NH3 that is attached to this. And the fifth one, I'll go up and down or down. So I'm going to put it down. And that will be NH3 here. So there's 5 ammonia that is attached. 1, 2, 3, 4, 5. Then the 6th attachment is the chlorine. This whole thing has a charge of +1. That +1 charge has a counter ion that makes the entire compound neutral. So the counter ion is bromine. Since bromine is sitting outside of the bracket, it's showing that it's going to be outside of the bracket over here, Br-. So this entire structure, this entire coordination compound shows that chlorine is in the middle and bromine is outside. Let's compare that to the one on the right. Try to draw this structure and then come back. So coming back, in this scenario, we have the bromine inside and then chlorine outside. So the halides, there's a interchangeable halide of the counter ion and the ligand that is inside. These are all the ligands, and this is the counter ion. So these are ligand, and the one outside is called the counter ion. So essentially what happened between the left and the right is that they have switched places. When there's a switch of the placement and comparing the two, we consider them as a coordination isomer. So by definition, coordination isomer are ligands. These are coordination compounds that have ligands and counter ions that exchange places. So these two are coordination isomer of each other. Then there is a relationship between a coordination isomer and also a linkage isomer. Now, before I tie the two together, let's talk about what linkage isomer is in the first place. Linkage isomer has a coordination compound. It has ligands that coordinate to the metal through different bonding sites. Here's what I mean. So here is cobalt. It's got the nitrogen, the ammonia, just ammonium 5, just like what we had in the before. But now instead of having that halide, it is NO2. Now I'm not going to draw it, but I'm going to give you the image of it. So here's my cobalt inside. Okay, and it's also got NH3 all around, ammonia all around. So if you're wondering why this is NH3 and this is H3N, it's just noting that the N is what attached to the bond to the cobalt, not the hydrogen. Okay, so it's also missing a bracket. So I'll add in a bracket here. And this has a charge of overall +2. The NO2, if you look over here, this is attached to the nitrogen. On the right-hand side is attached to the oxygen. So linkage isomers are isomers that will have these ligand coordinates that they can either attach to one element or the other element. So it's different bonding sites. If you look at these ligands here listed, which one can form linkage isomer? So we know off the bat, the nitrite ion we already use, we have the option to either to bind to N or to O. So out of all these, which compound can get it bind to? Well, I'll tell you which one, and we'll go over one by one why not the other ones too. So cyanide ion is one, and thiocyanate is the other. And we know already nitrite ion. Those three have the ability to do linkage isomer. That's because it could either attach to carbon or nitrogen for cyanide ion. For thiocyanide ion, it could attach to the sulfur or the N, or nitrogen. Notice I'm selecting the ones that have a lone pair. Now, why not the other ones? Well, if I were to attach to water, and you might say, well, can I attach to oxygen and the hydrogen? The answer is no. In order for it to be the ligand, it must have the ability to donate an electron. So here it has a lone pair that can be donated, but hydrogen does not. Ammonia, the N is the only one that could donate electrons. Fluoride ion, yes, all 4 of these electrons could be donated, but it's from just that one ion. Hydroxide ion, same reason as water. The oxygen is the only one that could donate electrons, so the center metal, transition metal, will never attach to the hydrogen. It'll be very much unfavorable. So let's kind of go back. The coordination isomer versus linkage isomer. Coordination isomer looked at two different, whether it's counter ion or the difference of the counter ion or the ligand. Here we're looking at the location of the ligand in itself. Where is it? Which element is it going to bind to? So we can say these two are linkage isomer of each other. So let's do, again, a review. A linkage isomers are the between these two. Coordination isomer, we're looking at the differences in the counter ion that exchange place with the ligand. There is a relationship I have mentioned before that between a coordination isomer and a linkage isomer. So they stem from what is called a structural isomer. Structural isomers, by definition, they have these are atoms with different connectivities. The structural isomer stems from what is called just an isomer in general. And isomers are compounds that have the same formula, meaning the same chemical formula, but they have different structures. So the chemical formula for, let's say, like these linkage isomer are exactly the same. There's 1 cobalt, there's 5 ammonium, and there is a nitrite, but the linkage is different. So that in general, a term is isomer. The isomer does split off into 2, structural, and actually there's another one called stereoisomer, which we'll cover in a different video. Okay, let's do a learning check. A compound has a chemical formula of cobalt, and there's 5 hydrates and chlorine and fluoride. Draw coordination isomers. Remember what coordination isomers are. They're the one that exchange the ions, the counter ions. So probably either chlorine or fluorine. They're the only guys that have a charge that will be a counter ion. So they're probably a replacement of the two. So if I were to actually write out the chemical formula with brackets, we can have cobalt and H2O5 and chlorine. And these are all inside the bracket and then the fluorine outside. Or we could have cobalt with water and then 5 fluorine and then having the chlorine outside. So let's draw the coordination isomer. The coordination isomers might look like this. So I have cobalt in the middle and 2 going back, 2 coming forward. I have H2O here on the corner, and instead of writing H2, I'm going to write OH2 to indicate that it is attached to the oxygen, not the hydrogen. Okay, now I have another water, so because I need to have 5 water total. I'll go down, and then here is my H2O. Okay, and I have my chlorine that goes on top. And these are all inside the bracket, and it has a charge of plus. And fluorine, since it has a charge of -1, right? Fluorine -1. All right, so you're going to try for this one and come back. So coming back, you can see the change of the counter ion, this fluorine here and chlorine over here now. All right, next one. A compound has a chemical formula of same thing, cobalt with 5 water, but then now you have thiocyanate. Draw linkage isomers. So this refers to location of the ligand. So if you look at SCN, so I'm going to go back to the previous slide, and it should show you all of these guys. That's some of the ligands are here. So thiocyanate ion has the ability to do either from the S or connect from the S or the nitrogen. Okay, so either one of them. So we're going to draw both of those with one of those connections. Let's do that. So same thing, we have cobalt, 2 going back, 2 going forward, and my H2O on all sides. And we have H2 on the bottom. Now we have thiocyanate, wherein which is going to attach to potentially S, C. I believe this will become a triple bond. Not required to know how it looks like, but this comes with practice. But as long as it shows that it's attached to either S or N, that'll be okay. And then or we have cobalt, same thing. Two going back, 2 going forward. OH2, OH2, H2O, H2O, and then H2O. And then now instead of attaching sulfur, it's going to attach to nitrogen. Okay. All right. So these are all possibilities of linkage isomers for that particular formula.